We have discussed amorphous and nanocrystalline silicon as well as various silicon alloys. In this video we will discuss a major challenge associated with using amorphous silicon. In this video you will learn about light-induced degradation in amorphous silicon, which is known as the Stabler-Wronski effect. You will learn what the Stabler-Wronski effect is and how exactly it affects the performance of a solar cell. The Stabler-Wronski effect influences the performance of amorphous silicon and silicon alloys containing amorphous tissue. The effect involves the degradation of amorphous silicon under the influence of light. Light-induced degradation was discovered by Stabler and Wronski 1 year after the first amorphous silicon solar cells were made, and is one of the biggest challenges for thin-film silicon solar cells. Because of the recombination of light-excited charge carriers, metastable defects are created in the absorber layers. The increased defect density leads to increased charge carrier recombination in the absorber, which degrades the performance of the cell. Let's look at the performance of an amorphous silicon solar cell. This figure shows a JV curve with the initial performance of such a solar cell. After about 1,000 hours of illumination, the efficiency of the cell stabilizes. We now introduce a stabilized efficiency of the same cell. We can see that the VOC is not significantly affected. The JSC, on the other hand, decreases due to the reduced charge carrier collection. The fill factor suffers most from the light-induced degradation, since the increased defect density in the bulk increases the series resistance of the solar cell. The stabilized efficiency is generally about 85 to 90% of the initial efficiency. But how exactly does the fill factor degrade during this 1,000-hour period? The simple thin film solar cell shown on the right with an amorphous silicon absorber layer is exposed to light under the standard test conditions. These are, as you may recall, 1 sun illumination, the AM1.5 spectrum and a cell temperature of 25 degrees. Note that the amorphous silicon of this solar cell does not correspond to the state-of-the-art material. The fill factor of this cell after deposition is about 74%. Upon exposure to light, the fill factor strongly decreases. We can discern 2 regions in this graph. The first 10 hours is where the strongest degradation occurs, since the fill factor is decreased from its initial 74% to about 60%. We can therefore call this the fast region. From 10 hours onwards, the cell degrades further, but at a reduced degradation rate. In this slow region, the fill factor decreases an additional 9% absolute, to achieve a stabilized fill factor of 51%. An interesting thing happens when a stabilized cell is subjected to a step of thermal annealing. As you can see, the performance loss of the cell can be reversed to a certain degree when thermally annealed. At 120 degrees Celsius, after a period of 30 minutes, the fill factor has been increased from 51 to about 62%. At higher annealing temperatures, yet more of the light-induced degradation is reversed, up to 97% of the initial fill factor. Unfortunately, after annealing, the cell will once more degrade when exposed to light. So what does this mean for the performance of thin-film silicon multi-junction devices? Shown here are a micromorph tandem cell and a triple-junction solar cell with an amorphous silicon junction on top, followed by 2 nanocrystalline silicon PIN junctions. The initial efficiency of the tandem cell is about 14%, while the initial efficiency of the triple junction cell is about 15.4%. In both devices, the amorphous silicon junction has a large share of the total power output. In the tandem cell, the amorphous silicon junction is responsible for about 2/3 of the total power output, while in the triple junction device, the amorphous junction accounts for about half of the output. It is therefore no surprise that as the amorphous silicon layer degrades, the performance of the device suffers. Consequently, the micromorph device has a stabilized efficiency of about 12.5%, while the triple junction cell has a stabilized efficiency of about 13.4%. In short, we have discussed how amorphous silicon and amorphous silicon alloys suffer from light-induced degradation, which is known as the Stabler-Wronski effect. Under the influence of light, additional defects are created in the bulk of the amorphous material, which degrade the JSC and foremost the fill factor of a device. We saw how the light-induced degradation is reversible through thermal annealing, and that the effectiveness of the thermal annealing process is temperature dependent. In the next video we will take a quick look at the processing of thin film silicon solar cells, both on a lab scale and on an industrial scale.